Hello wonderful person, this is Anton, and today we're going to be discussing the size and possibly the shape of the entire universe. Is our universe truly infinite? Does our universe have some sort of a shape we can describe or to some extent understand? And more importantly, do we have any observations or any data available to us that can actually help us answer any of these questions? Now, first of all, a lot of this is going to be based on this recent study that came out not so long ago that does actually try to answer this question. A study that does come up with a pretty interesting conclusion at the end. But before that, let's actually talk about what we've already known from some of the previous discussions. Previous analysis and various studies have already successfully determined that for the most part, the so-called observable universe, the universe that we can actually physically see, is approximately 93 billion light years across and could technically be defined as a sort of a sphere with us right in the middle. But it's important to understand that in this case, even if you were to leave this region and start, for example, somewhere right here, you would still find a very similar sphere around yourself in this new location, simply because we also believe that the universe itself, the unobserved universe, is a lot larger than the observed universe. And so if you were to find yourself in a new spot, you would simply have a new observable universe around you, which would still be the same size, approximately 93 billion light years across. But more importantly, the scientists studying the cosmic microwave background and also just trying to figure out the shape of the universe, time after time have determined that the universe for the most part seems to be what's known as flat. In other words, if you were to take two parallel lines and if you were to basically just have them go across the entire universe for as long as they could go, these parallel lines would never cross. And this implies the geometry of the universe for the most part is flat. It's not curved in any direction. Which of course also sort of implies that the universe could be, hypothetically, infinite. It could go in every direction forever. But the idea of infinity comes from math. The thing is, in reality, in real life, or at least when it comes to physical observations, we know that the idea of infinity usually just means that we don't really understand something, or new mathematics or new physics are needed to explain something. In this case, the universe might appear to be infinite, but in reality to be a loop. A loop that's not really geometric, it doesn't really change anything in terms of geometry, so parallel lines do still stay parallel, but a loop that's more or less topographic. Something that could be possible to imagine if we were to take a look at, for example, this right here, the Mobius strip. So for example here, you can still have two parallel lines that will stay parallel, but if you were to take a look at this from the topological perspective, from the outside, things would be a little bit different. The actual loop and the actual inversal becomes more apparent, especially if you look at this from an extra dimension. Now this is not something we can obviously do right now, or possibly ever, but this is sort of what's implied from some of the recent studies. In other words, you could still have a geometrically flat universe, but topologically it could be actually curved and potentially even create some sort of a loop. Which of course would imply that the universe has a finite size. A size that could still be growing because the universe is expanding, but a finite size nevertheless. Okay, before we go on, I know some of you might still be confused about this whole difference between geometry and topology. It is after all a somewhat complex concept, but I figured there might be at least one picture that could help you kind of understand all of this. This is actually from a computer science class from Berkeley University, and it gives an example of this from computer science. And so here is basically a good example of something that has same geometry but different topology. Both of these shapes geometrically look the same. But in terms of the actual lines connecting different angles, or in more computer terms, different meshes, notice how the connections are actually different. So these two shapes, topologically, are very different. But on the bottom here we have something a little bit different. They have exactly the same connections, same topology, but geometrically they don't actually look the same. And so in some sense you could maybe think of geometry as the actual shape of something, and topology as fundamental properties of some sort of a shape we're looking at. So for example, the connections, how they're made, and various other properties present in a particular shape. And so in this case, if for example our universe is this, a 3D torus or a donut, you could hypothetically change the geometry without affecting the topology. So in this case, the topology still is a donut, but the shape changes and the geometry changes as well. But by squeezing the donut, you do change the geometry and thus change some of the properties on the inside. Anyway, let's go back to the study. So in this particular case, the scientists really wanted to figure out the topology of the universe. So is the topology here of some sort of an infinite three-dimensional shape that just keeps going and going? Or is the universe some sort of a loopy shape that we can maybe somehow discover? And even though it's a great question, at the moment at least, it's a very philosophical question. If the geometry seems to be unaffected by anything, how can we possibly learn about the topology of the universe? Well, the scientists in this paper realized that maybe we can actually look at some of the earliest light in the universe. And here, it of course means looking at the cosmic microwave background. CMB has been used for a lot of different studies of the universe, but because this is the earliest light of the universe, it also allows us to see, to some extent, what the early universe was like. This is when we believe the universe was at least 1,000,000 times smaller than it currently is. And as you can see from these images, it's also not really that equal. It has a lot of different disturbances, it has a lot of different unusual formations, and a lot of different, what the scientists refer to as temperature gradients that are present in the cosmic microwave background. Now, as I mentioned in the past, it's already been used to sort of establish that the universe, geometrically at least, is flat after all. It does not seem to curve in any direction. But it turns out that because this also represents the universe when it was much smaller, if the universe is not infinite and if it's warped in any way, the actual shape itself back then would be much smaller as well, and would thus have sort of a limit to what sort of temperature gradient and what sort of different deformations would be possible in this early universe. So for example, in an infinite universe, we should be able to see all sorts of different representations of gradients, and all sorts of different waves should be possible because there's just no size limit. However, if the universe is indeed limited in size and does loop on itself, certain temperature gradients and certain deformations inside this early universe would actually have a size limit. Anything over a certain size would just not fit in this universe. Or in other words, the wavelengths of certain waves would simply be missing because they would just not fit if the universe was too small in size. And so, by using this assumption, the scientists in this paper decided to investigate this by trying to recreate some of the observations using computer simulations, and by then trying to modify the total size of the potential universe, and then seeing what kind of a cosmic microwave background it would produce. So for example, by changing the values of the size of the total universe, they were able to create different values for the CMB and different observable temperature gradients and deformations inside the universe. And by changing the values just enough, they were able to discover something that looked somewhat similar to the actual CMB as well, this picture right here. And what this particular figure shows us is a simulation of the cosmic microwave background produced if the actual universe was something that we would refer to as the three-dimensional torus. Okay, it's not really a donut. It's essentially a universe that sort of loops on itself no matter what direction you go into. So if you go this way, it's going to eventually loop on itself. If you go the other way, it's going to do the same. But because it's very difficult for us to imagine this shape, we're going to just refer to it as a 3D torus. And so if the universe was indeed topologically a 3D torus, and if this torus was about 3 times the size of the observable universe, this is actually what the simulation would produce. And in this case, the CMB seems to resemble the actual CMB we see in real life as well, with extremely similar parameters for different deformations and various temperature gradients. And according to the scientists in this paper, by modifying this further, by essentially letting the universe be infinite, they discovered that the best fit was still from a 3D torus of approximately 3 to maybe 4 times the observable universe limit. So essentially, if this is approximately 93 billion light years across, something that's roughly 3 to 4 times bigger would be the total size of the universe, according to the scientists in this paper. And furthermore, they even imply that the finite size, the topologically finite size, provides a much more accurate observations than the infinite size, which is a pretty interesting discovery. But there is a small caveat. All of this is based on the assumption that the instruments and of course the observations are absolutely correct. There's still a chance that maybe some of these observations are just missing those gradients simply because the telescopes were just not powerful enough. Maybe in the future, if we perform better observations, we might be able to discover these missing gradients and missing weights as well. For now though, this particular study and the implication from the study kind of does imply that the universe could be looped after all, and it could be some sort of a 3-dimensional torus-like shape. Now, as I said before, it's impossible for us to imagine this, simply because here we would have to think of this or look at this from 4-dimensional perspective. But it is nevertheless a pretty interesting discovery, a pretty interesting analysis, and a pretty interesting implication. Further studies will hopefully clarify this more. For now though, it's definitely something to consider and something to think about. But does all of this imply that if we were to basically leave our galaxy right now and travel in a single direction, that at some point in the future we might come back to the same point? Well, not necessarily. Remember, the universe is also expanding and pretty fast. As we leave our galaxy and as we start accelerating and traveling away from it, at some point the expansion is going to be so fast that we might actually not even see any more galaxies anywhere. And chances are, by the time that we actually get even halfway, based on our current understanding of how the universe is expanding, we're more likely to be completely stuck in space in the middle of nowhere. Not a single star, not a single galaxy in the vicinity. Now that's something we'll discuss more in some of the future videos, and something that I've discussed in one of the previous videos, the one where we imagine the universe 1 trillion years in the future. But for now, that's kind of all I wanted to mention in this video. Check out the relevant links and the study in the description below. Subscribe if you still haven't, share this with someone who loves learning about space and sciences, and maybe come back tomorrow to learn something else. Maybe support this channel on Patreon, or by joining the channel membership, or by buying the Wonderful Person t-shirt you can find in the description. Stay wonderful, I'll see you tomorrow, and as always, bye bye. Now this is totally not related to the study, but when I was super young, when I just learned about space and I think I just started to discover that we have planets and galaxies out there, I remember asking my mom, is the universe infinite? And because I was so full of questions my mom had no answers to, she basically just said yes, and kind of left the room and never talked about it again. But that simple yes created this fascination and a lot of sleepless nights when I would basically just lie down and try to imagine the infinity of the universe. I would try to fly really fast away from planet Earth just to imagine what it would be like, and I couldn't, and it drove me crazy. And ever since then I was wondering, is the universe truly infinite? Or does it loop? Or does something else happen? So maybe this particular study have finally laid it to rest. But future studies will definitely help us understand this in a little bit more detail.